All right, deep divers, welcome back. Today, we're going to be looking at something pretty wild.
Yeah.
It's artificial intelligence that can be designed to see,
Mm-hmm.
and not just like, in the way we think of, computer vision right now,
Right.
like recognizing a cat in an image. This is going way beyond that. You're
Yeah.
talking systems with artificial eyes and brains
Wow.
that could perceive the world in ways we haven't even imagined. And it's all because of this really cool research paper out of MIT.
Yeah, this is fascinating work. What they've done is really tap into the power of nature for inspiration.
Yeah.
Just think about all the different kinds of eyes in the animal kingdom.
Yeah.
The compound eyes of a fly,
Yeah.
the long-range vision of an eagle evolution has come up with some remarkable solutions over millions of years.
It's mind-blowing. Like I was reading about the mantis shrimp.
Oh, yeah.
They have like 12 to 16 different types of photoreceptors in their eyes
Wow.
compared to our measly 3.
Right.
And they can see ultraviolet and polarized light. We can't even perceive that.
It's incredible.
Talk about feeling visually limited.
Yeah, it really highlights the ingenuity of natural selection.
Yeah.
And that's what the researchers at MIT are trying to harness with this new approach they call GenVI, Generative Design of Visual Intelligence.
Okay.
They're using AI to accelerate the process of evolution,
Wow.
creating artificial visual systems that can rival or even surpass the capabilities of natural ones.
Okay, I am hooked. But how does it actually work? Are we talking about like robots with eyeballs running around?
Not quite robots with eyeballs, but you're getting closer.
Okay.
GenVI isn't just about processing images on a computer screen. It's about designing complete visual systems.
Okay.
With artificial photoreceptors that capture light and artificial neurons that process that information, just like a biological brain.
Wow.
The goal is to create systems that can interact with the world in a truly visual way.
So it's kind of like they're building artificial creatures with a sense of sight.
In a way, yeah.
That's wild.
They're designing these artificial visual systems and then putting them through these rigorous simulations to test and refine their capabilities.
Ah, so that's where the generative part comes in?
Exactly.
They're not just programming these systems with fixed rules, they're letting them evolve and adapt.
Exactly. They're using a process called the generation simulation selection cycle,
Okay.
which is essentially a digital version of natural selection.
Okay.
So imagine this, you have a generation block that proposes a bunch of different designs for the visual system.
Okay, so that's like our initial pool of candidates in our evolutionary race.
Right.
What happens next?
Then comes the simulation block.
Right, okay.
They take each of those designs and put them through their paces in a virtual environment. It could be anything from navigating a maze to identifying objects in a cluttered scene.
So it's like a virtual boot camp for these artificial eyes and brains.
Exactly. And this is where it gets really interesting.
Okay.
They can test out thousands of generations in a fraction of the time it would take in the real world.
Wow.
It's like fast-forwarding evolution.
But how do they decide which designs are the fittest? I mean, what are they aiming for?
That depends on the specific application.
Yeah.
Let's say they're designing a visual system for an autonomous drone.
Oh, okay.
They might set goals like avoiding obstacles, efficiently navigating to a target,
Right.
or identifying specific objects.
Right.
The simulation would then evaluate how well each design performs against those goals.
So it's like they're setting up a digital obstacle course and seeing which designs can complete it the fastest and most effectively.
That's a great analogy. And the designs that perform the best are then selected for the next round,
Okay.
the selection block. And here's the key part. The traits of these top performers
Yeah.
are then used to generate even better designs in the next generation.
Wow.
So the system is constantly evolving and improving, just like in nature.
It's like breeding a super race of seeing machines.
Yeah.
But isn't there a risk that these systems will become too specialized for the virtual world and won't work as well in the real world?
That's a great question, and it's something researchers are very aware of.
Okay.
It's called the sim-to-real gap.
Sim to real gap.
No matter how sophisticated our simulations get,
Yeah.
they can never perfectly replicate the complexity and unpredictability of the real world.
So how do they deal with that? Do they just cross their fingers and hope for the best when they take these systems out of the virtual sandbox?
Well, there are a few strategies they use. One is to make the simulations as realistic as possible,
Okay.
incorporating things like complex physics, diverse environments, and even a bit of randomness to mimic real-world variability.
Okay.
They're essentially trying to make the training as tough and unpredictable as the real game.
So it's like giving these AI systems a good dose of reality before they're unleashed on the world.
Exactly. And another important approach is to gradually transition from simulations to real-world testing.
Oh.
They might start with controlled environments and then slowly introduce more complexity and unpredictability as the system proves itself.
Makes sense. It's like training wheels for AI vision. But let's talk about the eyes themselves. What are these artificial photoreceptors actually like? Are they tiny cameras or something completely different?
They're more than just tiny cameras. They're designed to capture a much wider range of information about light.
Okay.
Remember how we talked about the mantis shrimp and its 16 types of
Oh,
photoreceptors?
right.
GenVI can create artificial photoreceptors that are just as diverse, if not more so.
So they could potentially see things we can't even imagine. What kind of information are we talking about?
Well, in addition to the basic properties of light, like intensity and color,
Yeah.
these artificial photoreceptors can be designed to detect things like polarization,
Okay.
which is the direction of the light waves,
Uh,
or even spectral information, which breaks down the light into its individual wavelengths.
okay. I'm going to need a bit of ELI 5 on that. What does polarization and spectral information actually tell us about the world? Why would an AI need that?
Think about it this way. Our eyes are great at what they do, but they only capture a small sliver of the information that's out there. Polarization, for example, can tell us about the surface properties of objects, like whether they're smooth or rough, wet, or dry.
Hmm.
It's used by some animals for navigation and prey detection.
Wow.
Spectral information, on the other hand, can reveal subtle differences in the composition of materials,
Oh, okay.
which could be useful for things like identifying different types of plants or minerals.
So we're not just talking about giving AI better vision. We're
Right.
talking about giving it a whole new way of seeing the world.
Exactly, and that's where things get really exciting by combining these novel photoreceptors with sophisticated artificial neural networks.
Yeah.
GenVic can create visual systems that perceive the world in ways that are fundamentally different from our own.
This is seriously mind-blowing stuff, and it makes me wonder if we can design AI that can see in ways we never imagined.
Mhm.
What other senses could we potentially enhance or even create?
Sure.
Could we develop AI systems that can hear sounds beyond the range of human hearing smell sense that are imperceptible to us, or even sense magnetic fields or gravitational waves?
You're thinking along the right lines. We're only just beginning to explore the potential of artificial sensory systems.
Yeah.
And GenVis is really pushing the boundaries of what we thought was possible.
It's an incredible time to be following this field.
It is.
You're telling me I can't wait to see what they come up with next, but we've covered a lot of ground already.
We have.
What are some of the key takeaways you want our listener to really grasp about GenVis so far?
I think the most important thing to remember is that GenVis is more than just a new algorithm or a piece of software. It's a fundamentally new approach to designing artificial intelligence, one that's inspired by the incredible diversity and efficiency of natural systems.
And it's not just about replicating what nature has done. It's about understanding the principles behind natural intelligence and using those principles to create something entirely new, something that could potentially surpass our own capabilities in certain areas.
Exactly.
Yeah.
And I think that's what makes GenVis so exciting and potentially transformative. We're essentially expanding our definition of intelligence beyond the human-centric view. We're opening up a whole new world of possibilities.
Well said. It feels like we're on the verge of a whole new era of artificial intelligence, one that's not limited by our own sensory limitations or preconceived notions of what intelligence should look like.
I couldn't agree more, and it's going to be fascinating to see how these advancements in visual intelligence translate into real-world applications.
Yeah.
I mean, the potential impact on fields like robotics, healthcare manufacturing, even art and entertainment is enormous.
Okay, now I'm really getting excited.
Yeah.
But before we get too carried away with the possibilities, let's dig a little deeper into how these GenVis systems are actually built and trained.
Okay.
It's one thing to talk about digital evolution and artificial eyes, but I'm curious about the nitty-gritty details.
Absolutely. Let's break down the building blocks of these artificial visual systems and explore the role of simulations in more detail. I think our listeners will be surprised by just how sophisticated these systems are becoming.
All right, deep divers, buckle up. We're about to go even deeper into the fascinating world of GenVis.
Let's do it. So you're curious about the nuts and bolts of how these GenVis systems actually work.
Exactly. We've talked about the big picture stuff like digital evolution and artificial photoreceptors,
Right.
but I want to understand what's going on under the hood.
Sure.
How do they actually translate these biological concepts into algorithms and code?
It's a fascinating blend of biology, computer science, and engineering. Remember we talked about artificial photoreceptors.
Yeah.
Those are essentially modeled as mathematical functions that take in information about light and output a signal,
Okay.
just like their biological counterparts.
Okay, so they're not literally tiny cameras, but they're represented as mathematical models that
Right.
capture the essential features of light.
Exactly.
But what about the brain part of the system? How do they simulate the complexity of a biological neural network?
That's where artificial neural networks, or ANNs, come in.
ANNs.
These are powerful computational models inspired by the structure and function of the brain.
Okay.
They consist of layers of interconnected nodes or neurons that process and transmit information.
I've heard of ANNs before, but I always get a bit lost in the technical details. Can you break it down for our listener
Sure.
in a way that makes sense even if they don't have a computer science degree?
Absolutely. Imagine a network of roads connecting different cities.
Okay.
Each city is like a neuron, and the roads are the connections between them. Information flows through the network just like cars traveling along the roads.
Okay.
At each city, the information is processed, transformed, and sent on to other cities.
Okay, I'm starting to get the picture. So these artificial neurons are like mini processing units
Right.
that take in information, do something with it, and then pass it along to other neurons.
Exactly.
But how do they actually learn? I mean,
Right.
how do they know what to do with the information they're receiving?
That's where the training process comes in. Remember the simulations we talked about
Yeah,
earlier?
yeah.
That's where the learning happens. They essentially feed the ANN with a ton of data from the simulation.
Okay.
And the network adjusts its connections, the strength of those roads between the cities, to improve its performance on a specific task.
So it's like practicing a skill over and over again until you get good at it.
Right.
The more the network sees and interacts with the simulated world,
Yeah.
the better it becomes at whatever task it's been given.
Exactly. It's a process of trial and error guided by feedback from the simulation.
Hmm.
The network makes predictions, gets feedback on those predictions, and then adjusts its connections to improve its accuracy over time.
It's amazing how they've managed to replicate this core principle of learning in a digital environment.
It is.
It's like creating a virtual school for AI vision.
Yeah.
But there's still a part of this whole process that I'm not quite grasping. How do they connect the artificial photoreceptors to the artificial neural network?
Okay.
I mean, how does the information from the eye actually get to the brain?
That's a great question. It's all about creating a seamless flow of information between the sensory input and the processing unit. Think of it like the photoreceptors acts as the input layer of the neural network.
Okay, so the signals from the photoreceptors are like the raw data that's being fed into the network.
Right.
What happens next?
That raw data is then passed through multiple layers of artificial neurons, each layer performing a different type of processing.
Okay.
Some layers might be responsible for detecting edges and shapes,
Uh-huh.
while others might be responsible for recognizing patterns or classifying objects.
So it's like a chain of command where each layer of the network builds on the information processed by the previous layer, extracting higher and higher levels of meaning from the raw sensory data.
Exactly. And the final layer of the network outputs a decision or prediction
Okay.
based on all the processed information.
So if the task is to identify a cat in an image, the output layer might signal, yes, there's a cat, or no, there's no cat.
Right, exactly.
It's like a relay race where the baton is passed from the photoreceptors to the various layers of the network and finally to the output layer, which makes the final call.
Right.
But isn't there a risk that these networks can become too complex and difficult to understand?
Sure.
I mean, if they're constantly adjusting their connections based on the data they're receiving,
Yeah.
how can we be sure they're not learning the wrong things or making biased decisions?
That's another crucial aspect of GenVI research, ensuring transparency and interpretability.
Okay.
Remember, these are complex systems, and it's important that we understand how they're making decisions, especially as they're increasingly used in real-world applications that affect our lives.
So it's not just about building systems that work, it's also about building systems that we can trust and understand.
Exactly.
But how do you actually make a neural network transparent? I mean, it's not like you can just ask it to explain its thought process.
It's a challenge.
Yeah.
But researchers are developing techniques to visualize and analyze
Yeah.
the inner workings of these networks. They're essentially trying to peek inside the black box and understand how the different layers are contributing to the final decision.
So it's like forensic science for AI trying to trace the evidence back from the final outcome to understand how the network arrived at its conclusion.
Exactly. And one approach is to create what are called saliency maps.
Saliency maps.
These highlight the parts of the input data that the network is paying the most attention to.
Okay.
So if the network is identifying a cat in an image, the saliency map might highlight the cat's ears, tail, and eyes,
Uh-huh.
showing that those features were most important in making the decision.
That's really cool. It's like seeing the world through the eyes of the AI, understanding what it finds most important. But let's go back to the simulations for a moment.
Okay.
We've talked about how they're used to train these networks.
Right.
Can you give our listeners some specific examples of what these simulations actually look like?
Of course, the type of simulation depends on the application.
Okay.
For example, if you're developing a GenVI system for an autonomous vehicle,
Right. You might create a virtual city with realistic traffic patterns, pedestrians, and weather conditions.
wow,
The system would then be tasked with navigating this virtual environment, learning to obey traffic laws, avoid obstacles, and make safe decisions.
it's like a driver's ed course for AI.
Exactly. And for a GenVI system designed for medical imaging, the simulation might involve virtual tissues and organs,
Okay.
allowing the system to learn to identify abnormalities or assist with diagnoses.
It's incredible to think about the range of applications for this technology. It feels like we're on the cusp of a major breakthrough in artificial intelligence,
It does.
one that could have a profound impact on almost every aspect of our lives.
Yeah.
But I'm also curious about the limitations of simulations. Are there any situations where they just can't replicate the complexity of the real world?
You're right to point that out. Simulations are powerful tools, but they do have their limitations.
Okay.
One of the biggest challenges is capturing the full range of human behavior.
Yeah. People can be unpredictable, and it's difficult to program that level of nuance into a simulation.
That makes sense. It's like trying to predict the outcome of a sporting event or the stock market.
Right.
There are just too many variables at play.
Exactly. And that's why real-world testing is still crucial,
Yeah.
even for GenVI systems that have been rigorously trained in simulations.
Okay.
It's the only way to ensure that they can truly adapt and perform in the face of real-world complexity.
So it's a combination of simulations and real-world testing that will ultimately lead to the most robust and reliable AI systems.
Absolutely.
But let's talk about something else that's been on my mind.
Sure.
We've been focusing on the technical aspects of GenVis, but what about the broader implications?
Okay.
I mean, if we're creating AI systems that can see the world in ways we can't even imagine, what does that mean for our understanding of intelligence itself?
That's a profound question, and one that philosophers and scientists are grappling with right now. GenVis is challenging our traditional notions of what it means to be intelligent. It's showing us that there are other ways of perceiving and understanding the world, ways that might even surpass our own capabilities in certain areas.
It's both humbling and exciting, isn't it? We're essentially expanding the definition of intelligence beyond the human-centric view.
It is.
We're recognizing that intelligence takes many forms.
Yeah.
And that we can learn from these alternative forms of intelligence, even if they're artificial.
I couldn't agree more, and I think GenVis is just the tip of the iceberg. As we continue to develop more sophisticated AI systems, we're going to be forced to confront even deeper questions about the nature of consciousness, perception, and even what it means to be human.
It's a wild ride we're on, and it feels like we're only just getting started.
It does.
But for now, let's shift gears a bit and explore some of the real-world applications of GenVis. We've hinted at a few already, but I'm eager to dive into some specific examples and see how this technology is already starting to make an impact. Okay, so we've explored the inner workings of GenVis. You know, the artificial photoreceptors, the neural networks, the simulations, it's all incredibly fascinating.
It is.
But now I'm really curious to see how this is all playing out in the real world.
Right.
What are some tangible examples of GenVis in action?
One area where GenVis is already making waves is in robotics.
Oh, yeah.
Imagine robots that can navigate complex environments with the agility of a squirrel or manipulate delicate objects with the precision of a surgeon. GenVis is making those possibilities a reality.
You know, when I think about robots, I still tend to picture those clunky, awkward machines from old sci-fi movies.
Right.
But it sounds like GenVis changing the game completely.
It really is one of the biggest challenges in robotics has always been perception.
Okay.
Giving robots the ability to see and understand their surroundings accurately. Traditional computer vision systems have made progress, but they often struggle with things like varying lighting conditions, cluttered environments, and unexpected objects.
So they're kind of like a student driver who's great at following the rules, but panics when something unexpected happens on the road.
That's a perfect analogy.
Yeah.
And that's where GenVI comes in, by mimicking the robustness and adaptability of biological vision.
Okay.
GenVI is creating robots that can perceive the world with a level of sophistication that was previously unimaginable.
Can you give our listener a concrete example of how this is playing out in a real-world setting?
Absolutely. There's some exciting work being done with GenVis in warehouse automation.
Okay.
Imagine a robot that can navigate a busy warehouse, identify and locate specific items, and even pick and pack orders with incredible speed and accuracy. GenVis is making that possible.
That would be a game changer for so many industries.
It would.
But it's not just about efficiency, right?
Hmm.
I imagine GenVI could also make robots safer to work alongside humans.
You're absolutely right. One of the key advantages of GenVis is that it can create robots that are more aware of their surroundings
Okay.
and better able to anticipate and avoid potential collisions.
Yeah.
This is crucial in environments where robots and humans are working in close proximity.
It's like giving robots a sixth sense for safety.
Yeah.
But what about applications beyond robotics? I know you mentioned medical imaging earlier.
Sure.
Can you tell us more about how GenVI is being used in healthcare?
Absolutely.
Yeah.
One of the most promising applications is in medical diagnosis. Imagine a GenVis system that can analyze medical images like X-rays or MRIs
Okay.
and detect subtle abnormalities that might be missed by the human eye.
That could be a lifesaver, literally.
It could.
But I imagine there are some pretty high stakes involved in medical diagnosis, right?
Yes.
How do we ensure that these AI systems are accurate and reliable?
That's a critical question, and it's something researchers are taking very seriously. One approach is to train these GenVis systems on massive data sets of medical images annotated by expert radiologists. The goal is to teach the AI to recognize the same patterns and make the same judgments as a human expert.
It's like giving the AI a crash course in medical school, but at warp speed.
Exactly.
But it's not just about replicating human expertise, right? I imagine GenVid could also potentially surpass human capabilities in certain areas of medical imaging.
You're exactly right.
Right.
And it can process and analyze images at a level of detail that would be impossible for a human.
Wow.
It can also detect subtle patterns and anomalies that might be invisible to the naked eye. This could lead to earlier and more accurate diagnoses, potentially saving countless lives.
It's incredible to think about the potential impact, but it's not just about medical diagnosis, right?
Right.
I've also heard about GenVic being used in drug discovery and personalized medicine.
You're right. GenVit can be used to analyze vast amounts of biological data, looking for patterns and connections that could lead to new drug targets or personalized treatment plans.
Wow.
It's essentially accelerating the process of scientific discovery.
It feels like GenVis is opening up a whole new frontier in medicine, one where AI is playing an increasingly important role.
It is.
But I'm also curious about its potential in other fields like environmental monitoring or space exploration.
Sure.
Could GenVis help us see and understand the world around us in new ways?
Absolutely. In environmental monitoring, GenVit could be used to analyze satellite images, tracking deforestation, monitoring pollution levels, or even predicting natural disasters.
That's incredible. It's like giving us a global scale vision system
Right.
to monitor the health of our planet.
Exactly. And in space exploration, GenVit could be used to analyze images from telescopes or rovers, helping us identify potentially habitable planets or uncover the secrets of distant galaxies.
It's mind-blowing to think that GenVic could be our eyes on the universe.
It is.
But I'm also curious about the challenges and limitations of this technology. I mean, we've talked about the sim-to-real gap.
Right.
But are there other hurdles that researchers are facing as they try to bring GenVid to its full potential?
One of the biggest challenges is data. These GenVis systems are incredibly data hungry. They need massive amounts of training data to learn and perform effectively.
So it's not just about having the right algorithms, it's also about having access to high-quality data
Right.
that reflects the complexity of the real world.
Exactly. And that can be a challenge in some domains,
Yeah.
especially those where data is scarce or sensitive, like healthcare or national security.
That makes sense, but what about the ethical implications? I know we've touched on this briefly,
Sure.
but I think it's worth revisiting as we think about the broader implications of this technology.
You're right. As with any powerful technology, there are potential risks and ethical considerations that we need to be aware of, for example. We need to ensure that these GenVis systems are used responsibly
Okay.
and that they don't perpetuate or amplify existing biases.
So it's not just about building systems that work, it's about building systems that are faring unbiased and aligned with our values as a society.
Exactly. And that requires careful consideration and collaboration between researchers, policymakers, and the public We need to have open and honest conversations about the potential impact of GenVis and ensure that it's developed and deployed in a way that benefits all of humanity.
Well said. It feels like we're at a pivotal moment, not just in the development of AI, but in our own evolution as a species. We're creating tools that can potentially surpass our own abilities in certain areas, and we have a responsibility to use those tools wisely.
I completely agree. The future of GenVis and of AI in general is on our hands. It's up to us to shape it in a way that benefits all of humanity.
Well, on that note, I think we've reached the end of our deep dive into GenVis. It's been a fascinating exploration of the cutting edge of artificial intelligence and visual perception.
It has.
And I hope our listener has gained some insights into the power and potential of this emerging technology.
Me too.
And as always, we encourage you to continue exploring, questioning, and imagining the possibilities the future of intelligence is unfolding before our very eyes. And it's up to all of us to participate in shaping it. Thanks for joining us on this incredible journey. We'll see you next time for another deep dive into the world of science and technology.
See you then.